Okay, so in the last video, we saw how conversion influences molar amounts and molar flow rates. But what we really want to know is how conversion influences concentration. That's because rate expressions are usually written in terms of concentration, and that's the rate expression is what we need to learn how to design a reactor for a particular reaction. Concentration, of course, has two components. One is the molar term, and the other one is the volume term. So in this video, we'll see how conversion influences volume and volumetric flow rate. So as an illustrative example, consider the gas phase reaction, A goes to B plus C. And for the sake of illustration, let's imagine that this reaction is being carried out in a balloon. So let me draw a balloon. So this is our chemical reactor for this example. So I have a balloon. And it's carrying out a reaction. A goes to B plus C. So for the sake of illustration, let's assume that this reaction is being carried out isothermally. And we're also going to assume it's being carried out isobarically because the pressure inside that balloon, say I'm holding a balloon right here, is probably the same as the pressure in the room. And so the balloon will expand and contract in order to maintain that constant pressure. So that brings up another point. The balloon has non-rigid walls. The walls will expand or contract in order to maintain the pressure of the room, or an equal pressure with the room that it's in. So we have essentially here an isothermal and isobaric reactor carrying out a reaction. A goes to B plus C. So now let's consider the case where in our balloon, only species A is present initially. So initially only A exists in the balloon. And the reaction is going to be allowed to go to completion. And at the end of the reaction, only B and C are present in the balloon. And again, this is a gas phase reaction. So gas phase reaction, we're going to assume ideal gas conditions. At time equals 0, we can write an expression for the volume inside the balloon. So the volume, E1, is equal to N1, or T1 divided by P1, where N1 is equals to the number of moles of A initially, which is Na naught. When the reaction has gone to completion, we can write another expression. We'll call this V2 is equal to N2 R T2 divided by P2, where N2 is equal to the total number of moles of B and C, generated over the course of the reaction. So we're going to say NB plus NC. And we know that N2 then is equal to 2 times N1. And we know this by reaction stoichiometry. At the beginning of the reaction, we have only A. At the end of the reaction, we have B and C. 1 mole of A reacts to form 1 mole of B and 1 mole of C. So for every mole I had at the start, I now have 2 moles at the end. So N2 is equal to 2 times N1. And we also know, because of the assumptions that we made, that T2 equals T1. So let's say we're just going to call that T. And we also know that P2 equals P1. And so let's just call that P. So that would mean that V2 is equal to 2 times V1. So if we arrange those formulas, that means that the volume of the reactor at the end is 2 times the volume of the reactor initially. So the balloon has expanded by 2 times over the course of the reaction. So that means that as the reaction proceeds, as the conversion increases, the volume of the balloon is getting larger. So the concentration then is going to be getting smaller over the course of the reaction. So let's look at the analogous case in a flow reactor. So if I draw my flow system, and I'll carry out the same reaction. A goes to B plus C, and I'll say initially I only have A entering the reactor, some temperature and pressure, and exiting I have B and C, so my reaction goes to completion again. Exiting at some temperature and pressure, and we'll again say that the reaction is isothermal, isobaric, goes to completion. And I can again use my ideal gas law to write out the volume. So my inlet volumetric flow rate, and then my outlet volumetric flow rate. And since I'm making the assumption that T equals T naught, I have an isothermal reaction, and P equals P naught. Where again, FB plus FC by stoichiometry is equal to 2 times FA naught. So again, this is going to say that my volumetric flow rate exiting is equal to 2 times my volumetric flow rate entering. So if I were to go the way I get that is I take this term and I substitute it in here, and then I relate these two terms. So this R term is the same, the temperature is the same, the pressure is the same, but now I have a volumetric flow rate here equals 2 times FA naught, and over here I have a volumetric flow rate equals 1 times FA naught. So that says that the volumetric flow rate exiting is twice the volumetric flow rate entering. So as inside the reactor, reaction is carried out to some conversion, and that causes the volumetric flow rate to change. So a key point here is that this is only for gas phase reactions. So as if you have a reaction where the number of moles on the reactant side and the number of moles on the product side are different, then this changes the number of moles in the system, and hence it changes the volume or volumetric flow rate. The exception is a constant volume batch reactor. If you have a constant volume batch reactor, then it doesn't matter if the number of moles changes from reactants to products, then it's still constant volume. In that case, the pressure would change due to the change in the number of moles. If you have a liquid phase reaction, then it doesn't matter if the number of moles changes in your chemical reaction. You can always, in this class, assume a constant volume or constant volumetric flow rate when you have a liquid phase reaction. The exception is if you have a semi-batch system. In a semi-batch system, you might be adding liquid or drawing liquid out. Of course, you cannot assume constant volume in that case. And as long as there are no phase changes, so think about a phase change. If you have a cube of ice, for example, in your reactor, and over the course of the reaction, that ice melts, then the volume of your system, if your system was the ice, has changed dramatically. But as long as that isn't happening and you don't have a semi-batch system, then you can assume constant volume in a liquid phase system. So you're essentially assuming that volume expansion contraction due to mixing is negligible. You're assuming that the density of the system with temperature is pretty constant, and those are all very reasonable assumptions to make. So in this class, we can always assume constant volume or volumetric flow rate when we have liquid conditions, except when the reactor is a semi-batch reactor. So that's all I want to say for this lecture. In Canvas, I've summarized the formulas that you can use to account for how conversion influences volume and volumetric flow rate. There's actually formulas for the cases where you can use conversion to solve your problems, and then there is also formulas for the case where you cannot use conversion. I encourage you to have a look at those formulas, as those are what we will be using throughout this class to account for how the influence of conversion on volume and volumetric flow rate.